Hi, electrical circuits. Let's go ahead and talk about electrical circuits. Let's go ahead and continue our work through chapter 20. We're going to talk about section B, electrical circuits. All right. Well, recall from chapter 19 that there are two ways of connecting multiple electrical components together. You can connect them in series or in parallel. A series circuit has a single path for the current. So here, example A or diagram A, this is an example of connections done in series, where there is one path for the electrical current I to go. Let's say it starts here at this point, it goes up here through each of these boxes and goes back around to where it started. And because it is a circuit, it's going to be a closed path that's going to keep going around and around and around. Or we can connect these components, these little boxes, in parallel formation, where they are running alongside each other. Now, this current, let's say it starts in the bottom left corner, it goes up and then this way, and it actually can go through three different paths. It can go up here, through the middle, or down here. And this one current, the single current, splits into three different currents, and then comes back around here, and then it goes back around. Now, it might be helpful to think of this as kind of like water. If you think of these currents, like this electrical current, as water, if you have water flowing through a pipe and then it has a choice to go in three different paths, all right? I mean, it would split up. But eventually they're going to go ahead and combine to make one current again, and it would just keep flowing around and around forever. Now, let's go ahead and just dive a little bit deeper into series circuits. All right, well, I know you want to talk about parallel circuits more. I know that's more interesting. Don't worry, we'll get back to it. Let's talk about series circuits just for a minute. Well, electrical potential is higher just before a component than compared to just after the component. This decrease in potential is called a voltage drop. So the electrical potential, or sometimes we call that voltage, is higher just before a component than just after the component. So make sure you copy down these notes, and then we're going to go ahead and look at a little illustration to kind of show that point. Now, here is an example of a circuit in series, right? Where this current is going around this way and going back around, and around. Now, what we just said was the electrical potential is higher just before the component. So let's say we're starting here at this bottom corner, or let's say we're starting here. And as soon as it crosses this point right here, it's going to get a voltage rise. We can pretend like this is a battery and we're injecting some voltage into this. There's a voltage rise. And then when it comes across here and goes through here and it goes right before this point, the voltage is still the same. Let's say that this was 2 volts. All right, 2 volts is traveling, 2 volts is traveling, and when it crosses this component, the voltage is going to drop. All right, let's say from 2 volts to 1 volt. Okay, so as it crosses here, it went from 2 volts right before. Remember, we said the potential, electrical potential is higher just before. So it's at 2 volts. So when it crosses this point, it drops down to 1 volt. The 1 volt is traveling, and because it's crossing a second one, it's going to drop down to 2 volts, or drop down from 1 volt to 0 volts. And now it's going to go ahead and transfer here, and then when it hits this, it's going to get 2 volts back. So 2 drops to 1. 1 drops to 0, 0, 0, 0, 0, 0, then it adds 2 again, and the circuit continues to go. Now, this is what we call voltage drop whenever it goes through series. You can think of this kind of like potential energy. Now remember, potential energy, when we talked about a long time ago about potential energy was, let's get this pen. U is equal to mgh, and this was potential energy. And potential energy depended on the height. The higher a box was, like if we had a box up here, it has more potential energy. And as it drops down, drops down, drops down, it goes back down to 0. But if I put that box back on the top, the potential energy is all gained again. Similar concept with voltage. Alright, it has an amount of voltage, and then it moves and it drops, then drops even lower, and then it gets it all back when it goes back to the voltage rise spot. Okay, so this is how voltage is illustrated when we are in series. Now, when we are parallel, alright, the current of the whole circuit is just going to be all of them added together, right? And the potential difference is the same across all parallel paths. So there's not going to be a voltage drop. It's going to stay the same. Okay? So that's kind of the big difference between parallel and series circuits when we're talking about voltage. Now here are some key symbols that we should kind of get used to, because often in this type of work through physics there are a lot of diagrams that are drawn and we have to know what these are. Now this is a DC voltage source. DC stands for direct current. So kind of like what I was talking about earlier when we had a voltage rise, if it went through this part, it had a source of voltage, right? This is an example of what you would call a battery, right? If you ever see these lines, it's a battery. Current is represented by the letter I. This is a resistor. This squiggly looking line is the symbol that we use for a resistor. This is the symbol that we use for a capacitor. And then this is a switch. Now, a switch is used to start and stop current flow by opening and closing the circuit. Now this should make sense, right? Because in order for us to have a circuit, it has to be a closed path. And let's pretend that we had a current going through this line, and as soon as it hits to this point right here, it's not connected to anything. So because it's not connected to anything, it's not going to go anywhere. Now, if we turn the switch on and this line moves downward and connects, now the current can go ahead and travel. Now, let's go ahead and talk about equivalent resistance. For series resistances, current is uniform. The sum of voltage drops across each component equals total voltage drop across all series components. So, like looking at this picture right here, this is an example of a battery, right? So that's the voltage source through a battery. The voltage source is going here. The current is traveling along this path. There's a voltage drop, voltage drop as it goes through the resistors, and it comes back around. Now this voltage is equal to these total voltages all just added together. The total voltage is just going to add all of these voltages together, right? And then it gains it back as it goes through the battery. Okay, now when we have voltage, you just add them together. When you have resistances in series, you have to, well, I guess you can add them together to get to. The total resistance in series is the sum of the individual resistances. You're just going to add them together. Now that's a little bit different than when we're in parallel. But remember, when we are in series, like in this illustration, all right, we're just going to keep adding everything together. Now, what if we have some resistances that are in parallel? Well, the voltage drop is equal in each branch, and the sum of the current in branches is equal to the current entering the divided circuit. Here's a diagram that illustrates this point, where I have a battery here, or that is our voltage source, and the current is flowing in this direction. As it hits this little dot, this dot's called a node, right, it's going to split into 3 different paths. We have current 1, current 2, and current 3. Now, If you look at this, the total current is just all of these currents added together. The total voltage is equal to one of this volt. They're the same voltage that's going all the way through. There's no real change. They're all equal to each other. And notice the resistance is no longer just adding them together. It's not resistance 1 plus resistance 2 plus resistance 3. When they are parallel, when they're next to each other, like they are illustrated here, then you have to find the reciprocal of them. In this case, it would be 1 over R1 plus 1 over R2 plus 1 over R3. Now, I'm going to go ahead and help you out with this just a little bit, just because I know this can be kind of confusing with this whole reciprocal thing. So I'm going to go ahead and just make an example. Let's say that this resistance was, let's say, 2 ohms. And this resistance was 2 ohms. And this resistance was 2 ohms. Now, what would the total resistance be? Well, 1 over R total is equal to 1 over 2 ohms plus 1 over 2 ohms plus 1 over 2. Alright, if I add these together, because they're a fraction, they have the same denominators, this is going to be 3 over 2 ohms. Okay, so 1 plus 1 plus 1 is 3. And because we're adding fractions, the denominator stays the same. So, what is a total resistance? Well, the resistance is a reciprocal. So because this is math and math is fair, if I wanted to move this, if I wanted to reciprocate this side, move the R to the top, I would have to reciprocate, find the reciprocal or the refliprocal or the reciprocal of 3 over 2. So that means the total resistance is just going to be 2 over 3 ohms. Alright, so all I had to do is flip them around. Once I add the fraction, I can just flip them around and I would get the total resistance. Alright, adding more resistors decreases the total resistance. So we had 2 ohms in each of them, and we ended up with 2 over 3 as a total resistance. So we did see that it dropped a little bit. Resistance problems can be simplified in steps using equivalent resistors. Basically, you can, like if you have a really complicated looking one, you can calculate the values of parallel resistors, and then you can add them to the series resistors. And then I already talked about this, but a node is a place where the current divides or converges. So like in this example, these little dots are the nodes. Parallel paths begin and end at a node. So let's go ahead and talk about how to hopefully figure out these series equivalent resistance. All right, I'm going to start here with this battery, this voltage, and I want to try to figure out what are all of these. Like this looks super complicated with all these different resistors on here. But I do know that these two guys are what we call in series. All right, it's like a train or like a domino. It's going from this guy to this guy. And whenever we have them in series, we can just add them. So 0.5 ohms plus 0.5 ohms equals 1 ohm. That wasn't that bad, right? So I know that this guy, this resistor, I can replace it and I can say that this is just 1 ohm. All right? 0.5 plus 0.5 is 1. All right, and that guy went there. Now, we have this guy, and these are what we call parallel. So we have 1 over 6 plus 1 over 6 plus 1 over 6 is equal to 1 over the total resistance. So this is 3 over 6 is equal to 1 over R. And if I find the reciprocal and the reciprocal, then I figure out that 6 over 3 is equal to R, so that's the same thing as 2 ohms. So I can replace this with just 2 ohms. Alright, so it's really not as scary as what we thought, and now I have a resistance of 1 plus 2 plus 8, and then I'd have to simplify the rest of these. So it looks scarier than what it is. You're just using 2 basic rules to figure out, how to simplify them. And at the end of all of it, you can just say that all of these resistors are equivalent to like 1 resistor depending on what they all add up to. Now the next few slides are going to be slides that have a lot of rules for you to copy down. So if I read these too fast and just kind of move on to the next slide, just pause it and just copy these down into your notes. But they are important rules for us. I think this is more background information because we're not going to be doing a whole lot of math with these things, at least not in this class. If you guys go to college and take a college physics class, you guys will go more in depth on these. But at least copy down these next few slides and then we'll be done. So the rules for current and potential difference in series and parallel circuits can be summed up by two general rules called Kirchhoff's rules. Kirchhoff's rules. So number one, the sum of voltage drops in a simple closed path equals the sum of voltage rises in the path. A simple closed path does not contain any cross-connecting paths. All right, rule number two, the sum of currents entering a node equals the sum of currents leaving the node. Remember, the node was like the junction point when it splits up into parallel. So the current entering is equal to the current leaving. So those are the two main rules. Now, we can also look at this saying the algebraic sum of the voltage drops and the voltage rises in the path is zero, meaning that that when it crosses a battery or a DC power source, voltage source, then it's going to rise, and then when it goes through the resistors, and then it's going to fall, right? And at the end, it's going to balance out. The algebraic sum of the currents entering and leaving the node is zero. So this is the same thing. These two rules are the same things, just kind of restated. Now, positive and negative signs must be consistent whenever you talk about this, meaning if you are saying that a voltage is positive going one way, it has to be negative going the opposite way. And same thing with, just make sure you're consistent. So the change in voltage is equal to the voltage out minus the voltage in. Okay, almost done. The last thing we need to talk about are a few different electrical instruments. Commonly used electrical instruments whenever working with circuits. To calculate any quantity associated with a circuit, you must have some information. You will usually obtain this information by using instruments to detect basic quantities. An ammeter measures current. A galvanometer is a sensitive ammeter for detecting very small currents. And devices to measure current must be connected to the energized circuit in a series with the current being measured. An ohm meter measures resistance. So looking at these three, we have one more to talk about in the next slide, the last slide of the lesson. But these look like really good fill in the blank or multiple choice type questions, especially on your homework and or quiz. All right, so ohm meter measures resistance. The last one for us to talk about is a voltmeter. A voltmeter measures the voltage drop or rise across an energized circuit component. The instrument is connected to the circuit in parallel with a component for which the voltage is being measured. So a voltmeter measures the voltage drop or rise. Okay, that's it for this lesson. Hopefully you enjoyed it. Hopefully you learned a lot about circuits. I know we haven't really talked about this really before, so this is kind of new for you guys. I think you guys will be fine. All right, see ya.